Hey there, everybody. Welcome back to Sustainable Design Masterclass. It's always great having you here. We got folks streaming in from all across the world. Today we have Walter Jehne. Walter, am I saying your last name right? Is it?
Yeah, look, that's great.
Okay,
Really?
Walter Jehne. Yeah. But awesome. This is great because this is very short notice we did this. But we got a great response. We got dozens of people writing in, a few hundred have signed up because water is a super important topic for all of us. This concept of water restoration. So yeah, tell us where everybody, if this is your first webinar, tell us where you're coming in from. I'm coming in from Berkeley, California. And Walter, where are you coming in from right now?
Well, look, we're in Canberra in Australia, the capital city of Australia, and it's basically a beautiful summer's day down here. Obviously, you guys have been having a lot of cold weather up there, but it's hopefully about 40 degrees centigrade later on this morning.
Oh, man.
Yeah, global warming.
Yeah, no joke. All right, so we got folks coming in from Canada, from Arizona. Awesome. Vermont. Maryland's coming from Vermont. Elaine from Ontario, Canada. Kat from Vermont. Awesome. A lot of Vermont folks here. This is great. Dusty coming in from Germany. Fantastic. Katie from Queensland. Awesome. So it sounds like it's a nice mix of folks from all over North America, from Australia, from New South Wales, and we got Boston. So this is fantastic. Without further ado, why don't we just get started? So hey there, everybody. I'm Raleigh Latham. I'm joined by my partner with Sustainable Design Masterclass, Neil Spackman, and we're doing a series of webinars starting today on the concepts of water restoration. Some people call this the new water paradigm. Walter is going to explain his processes behind it. And this is absolutely incredible. These incredible concepts will blow your mind about the importance of water in our climate cycle and how it is one of the most important solutions we have on the local level to repair ecosystem health. This is absolutely incredible, and I'm stoked to start a series of webinars on this. So just for folks who haven't been here before, to get the most out of this, make sure you turn off all those stupid distractions. You got Facebook, turn it off. You got a phone on Instagram, just throw that across the room, stomp on it for good measure, because you want to absorb all of Walter's incredible knowledge. He's got more than 40 years of experience. And thanks again for joining us, Sustainable Design Masterclass. I'll let Neil take it from here.
All right, thanks, Raleigh. Shout out to you for helping put this all together. To Russ Spear as well, who introduced us to Walter. And I'm seeing a number of people actually that we're hoping to have on in the future. So welcome to everybody. Walter, you actually popped up on my radar quite recently. It was only a couple months ago where I saw a YouTube video of you doing a lecture with a whiteboard, and I watched it and I was like, yeah, this seems up my alley. And then it was only a week or so later that we got an email introducing you to us, and I was like, this is very serendipitous. So we're pleased as punch to have you on here. Welcome to everybody else attending. Walter, we're going to let you take it away from here.
Okay, thank you very much, Neil. Thank you very much, Raleigh, and good morning, everybody. It's morning here in Australia, but obviously afternoon or whatever elsewhere in the world. Just by way of introduction, I'm a soil microbiologist, worked for a long time in our CSIRO, which is our government leading research institution in Australia. But then I've also worked in government for a long time with innovation commercialization at a much higher strategic level. But for the last 15 years, I've been retired, and we formed this little group called Healthy Soils Australia. And it's very much involved with getting down to practical grassroots regeneration and really addressing the fundamentals that we in Australia are facing, but of course the whole world is, in terms of climate change, but particularly the grassroots issue of aridification, desertification, and how do we look after the water, the food, the biosystems, habitat, and at the end of the day, that whole social stability, how do we keep communities, nations, basically the biosphere functioning. And as you all know, look, climate change is really the key thing that's impacting all of us, but it's doing that actually not just through the carbon cycle. I mean, obviously CO2 is going up, but it's really the hydrological aspects of killers, and I mean killers, because it's the actual storms, the floods, the droughts, the aridification, the wildfires. They're the things that impact communities and biosystems, and they're the things that are actually accelerating dangerously now. And we've been in about 50 years of warning on this scientifically, and of course we've always just kicked the can down the road. Oh, well, look, the politics will do something in the future. But it's getting to the point now where we really need to address things locally at the grassroots level to start regenerating resilient biosystems. And it's really empowering communities to do that, because unless we do that, effectively we're cactus. There are 7 missed meals, basically, between social stability and crisis. And so really we've got this whole situation. There's 7.4 billion of us on the planet now, 10 billion projected by mid-century. And so unless we address that water, that food, that whole social stability issue through this regeneration, we won't be able to sort of make sure that those 7 missed meals and that social stability is there. So bringing it all together, really, what do we do as communities, as people on the ground, farmers, activists, and what have you, to help in that? Because in a sense, you know, like crowd control and more security at the police level won't help us. So what is it that we can do? And in a sense, we have 3 urgent imperatives, both in the short, medium, and long term. Clearly, in the short term, we have to address this water, food, habitat, stability issue, right? That's happening now. Basically, communities, nations, regions are falling apart, not just in the third world, not just elsewhere. I mean, California, what you've experienced there is something that is really serious. And unless we get to unless we get to grips with that and basically find ways of fixing it, it's really, really worrying, because basically, you know, California is aridifying, and unless we find ways to rehydrate California in the next 10 years, systems will just fall apart. On the medium term, we also have to look at actually something that we can do to cool the climate. Okay, we've basically got now locked in global warming. Okay, that's going to continue for decades and centuries. We'll go into that a little bit detail later, but we've got to find some way, how do we actually safely and naturally cool the climate? And of course, to do that, we've got to go back to nature and say, well, look, how has nature over 4 billion years regulated the climates and the temperature and the heat balance of this planet? And what do we do how do we learn from that? But also, how do we then apply that knowledge? And that's really going to be the guts of what we'll be talking about today. Again, we have to do that, because otherwise the default option is already being talked about elsewhere, preventive geoengineering. And that really is a very, very serious and dangerous slide to very serious problems. In the long run, though, we've also got this big picture, but it'll all come out of what we've been talking about. How do we regenerate resilient biosystems? And basically, if we can do that, how do we bring this whole global situation to a equitable soft landing? You know, like give dignity, equity, but also basically try to find some transition to a sustainable, just society. And long term, of course, that is achievable, that is the goal, but only if we take and address these short-term, medium-term issues. We're also not naive, of course. We have to do this in the context of major impediments that exist. And obviously, you know, we've got the dogma, we've got the inertia, we've got all the vested interests, we've got all the sort of problems of politics, the short-termism of politics, and we've also got the situation of completely false accounting. where we don't recognize the natural capital values in ecosystems. We just externalize all our impacts. We don't consider risk issues at all. And of course, that has completely led our economics up the garden path into this crisis. And so again, what do we do at that level? But these are impediments, and the bottom line, we have to get around them. But we have to actually now, in a sense, look at empowering local, regional communities to take the lead in this, because it's not going to happen. It hasn't happened for the past decades. So really, it's up to us or nothing. There's no question that nature will always be there, and there's no question that nature will fix this problem. It's only a question whether nature will fix it with us or after us, once we've sort of completely messed up the show. Okay, so basically it comes back to nature. And you see, as a soil scientist and as a long-term ecophysiologist, we started off with a planet which was basically just rock and ocean, 400 million, sorry, not, 400, up to 400 million years ago. That's all it was. And basically, soils formed 420 million years ago through the symbiosis of fungi and plants and created the biosystems, because it was actually the formation of these, the soil carbon soils that allowed then water to be retained on land, nutrients to be made available, and from that we had the rapid evolution of productive biosystems all across the land surface. And so really nature has shown us that yes, it has this amazing regenerative capacity through petagenesis, through plant successions, and really that's been the thing that's made our biosystem, it's made our hydrology, it's actually made and governed our climate, and really it's the tools that we have to respect and use to restore it. And in a sense, that's a challenge that we have in front of us. So how do we understand nature and how do we use its processes to restore that? And all we're doing is really just looking at those natural things and saying, okay, well, where do we intervene? Where have we intervened in the past? How we've disturbed and degraded this? But how can we actually now use that same knowledge to actually rebuild, restore, regenerate? And how can we do that? Basically, there's another important thing. How do we do this in the space of the next decade or decades? Because that's all we've got. Certainly nature's had millions of years, but it too can do a lot faster. But really our challenge is how do we do that faster? And really it just comes back to basically, and we've got the slide of the water cycle up here, it really comes back to climatology 101, right? It's really the whole thing. Here is the global water cycle, and basically it is this water cycle that has been fundamental in creating the terrestrial biosystem. But what we don't understand is this water cycle that also governs, in a sense, the climate. This is a water cycle that regulates the climate. This water cycle actually drives 95% of the heat dynamics of the blue planet, okay? And so it's the engine room, it's the driver, it's the means through which this whole ecosystem on planet Earth hangs together. The carbon dioxide component of this global heat dynamics is also, of course, important, but it represents about less than 4% of that heat dynamics. And actually, in the political thing, it's important to recognize that, sure, we've been focused on Charles Keeling. Yes, CO2 is going up abnormally because of what we've been doing. So we focus on the symptom, carbon dioxide, and we say, okay, what do we have to do to reduce CO2, which we must do, but it's only 4% of the global heat dynamics. And in a sense, the point is, and it's important globally, that 4% isn't going to get us out of the mess we've made. Okay, it's far too late, and the CO2 response is going to be far too limited to be able to change and prevent dangerous extreme climate changes. And so now we've got to face the reality that, okay, if we can't do it just through CO2, how do we do it through the water cycle, as nature did? And in a sense, it's looking at those elements of the water cycle in some detail that, in a sense, I want to go through, because they provide us with the tools, the empowerment, the solutions to regenerate Earth and to actually bring this whole climate story, but also the food, the water, the biohabitat, the social stability consequence of that climate cycle back into balance. And quite frankly, it's it. If we can't do that, it's cactus, and then we'll just have to get out of the way and nature will do it after we've gone. Okay, so I suppose we can sort of start saying, well, what is the basis of the water cycle? It's quite complicated. There's many parts and stages and variable factors that affect it. And in a sense, it's been both its strength naturally, but it's been its problem because it's so complicated and variable that we haven't been able to model it easily mathematically. And so, in a sense, the climate community has tended to ignore it because it's too complicated and it's not, easily modelable. It can't be modeled easily. And yet, if we take it perhaps as not at a child's level, but if we take it at the very simplistic level and we say, look, here's a water molecule, and if we take that water molecule on a journey as it goes through this water cycle that Rala has put up for us, then I think we can get some understanding just how powerful it is and how by intelligently using it and restoring natural balances as it's used, we can actually not just cool the planet, but provide the water, the food, the future we all need. So to start off with, and this is really the first thing, obviously we know that water evaporates and transpires from the land surface up into the air as part of that natural process. And again, we've got this evapotranspiration coming off the land surface. Every gram of water that is transpired up in the air has to turn from liquid to gas. And to do that, it has to take up to 590 calories of heat energy from the Earth's surface to vaporize it and transports that heat energy from the Earth up into the atmosphere. And so obviously it has a massive, powerful cooling effect. Okay, because every gram is taking 590 calories of heat energy, cooling that surface in the consequence. And that's basically really important because in the big picture, we've got the sun up here, and obviously the sun is giving us constant incident solar radiation, about 342 watts at the top of the troposphere. And of course, to maintain heat balance, the Earth has to actually re-radiate 342 watts back out to space. Otherwise, it would heat up dangerously. And of course, it's done that balance naturally through these water cycles for 4 billion years. Okay, and this evaporation, transpiration, latent heat flux, we call it, that flux basically takes 24% of that incident solar radiation that the Earth receives and takes it from the surface back up into the atmosphere. Actually, it's another sort of background context thing. We've basically had this balance between 342 watts coming in and 342 watts going back out. But because of our human-induced greenhouse effects, we've basically prevented some of that heat escaping back out to space. Basically, we've prevented about 3 watts per square meter, or less than 1% of that incident heat getting back out to space. So the challenge now is to basically say, okay, how do we get that 3 watts per square meter extra heat back out to space? How do we restore that balance? And in a sense, this transpiration can help us do that because it's going to take heat from the surface up into the atmosphere, thereby cooling it. But we've got to go further. And so that's the next stage in the cycle. At this point, let's just say this evapotranspiration cooling the surface has been well described. There's a whole lot of people, Michael Kravchuk, Willie Ripple, and others who've been talking about that as the small water cycle, and totally valid, totally important. And so that's a key component. But in a sense, there's 10 stages to this global water cycle, and this is just one of them. So definitely important, but basically I'm just taking it further because yes, that will cool the surface, but the next step is that water will be in the air. So what happens to that water in the air, and how do we actually complete that cycle? So the second part of this water cycle actually is, yeah, we've now got this water in the air. And of course, this is really where it gets dangerous, because that water vapor that's gone into the air is actually the major greenhouse gas. So that water vapor that's gone into the air is actually the most powerful gas absorbing long wave infrared energy that's been re-radiated from the surface in the greenhouse effect. Water vapor represents, easily 60% plus of the greenhouse gas effect. CO2, by comparison, is about 20% of that gaseous greenhouse effect. So, it's basically a 3-to-1 or more factor. And that water vapor not just only is a leading greenhouse gas, but while it's in liquid micro droplets, while it's in hazes in the air, and you'll know that basically in the morning you'll often have clouds or hazes or mist, well, the water then is in little micro droplets, very small haze droplets. That water is also absorbing incident solar radiation. So in a sense, that water in the air has a dual heating effect, both through the greenhouse effect and through this warming effect. And so while we've lost up to 80 watts per square meter through the evapotranspiration latent heat flux thing, these water vapor molecules in the air may be sort of then absorbing up to 70 watts per square meter while they're in the air. So the quantity and persistence of that water vapor in the air is a very, very major heat governing factor. The issue is, naturally, that was very important because it was that natural humidity in the air that has enabled this planet to maintain a temperature 33 degrees centigrade hotter than it would have otherwise been if it didn't have that atmosphere. So in a sense, it's that water vapor in the atmosphere and that heating effect that has actually warmed or kept the Earth at a higher temperature than otherwise, that has enabled oceans and liquid water to be maintained on the Earth's surface continually for over 4 billion years. And of course, it's the thing that's enabled life to evolve initially in the oceans and then onto land. So, the Earth wouldn't be the Earth without that warming effect, that natural greenhouse, that natural warming. But obviously, we've now overshot that. So the question is, why has this heating effect got more intense? And it's got more intense because the amount of water that's in the air has increased significantly over the last decades. And why it's increased is we're putting up more aerosol nuclei than we did previously. And so we have these persistent humid hazes that maintain that higher water content in the atmosphere. Up to 4% of the air of the atmosphere can be water vapor by weight. So if we have all that, we just end up with a lot of heating effect. So in nature, then, of course, it was critically important to reduce how much water is going up into the air by reducing the amount of aerosols that nucleated that water, but also to basically get that water out of the air. And these are subsequent parts to that water cycle and that cooling cycle. So I hope this isn't getting too complicated, but certainly basically it's cooling as the water goes up from the air, but then we've got this dual heating effect of the water in the atmosphere, in the lower atmosphere, in these humid hazes. they're getting very, very dangerous. In parts like the Middle East, we've got now this situation in summer where we end up with, 40 degrees centigrade temperatures and 90% humidities, and that's now starting to exceed thresholds where humans can live and survive. Because once we get over 37 degrees centigrade and we haven't got the capacity to cool by evaporation, perspiration, then it goes beyond the physiological limits of human, heat balance and survival. So we're getting to the point now where if we don't do something about this in these regions, we just can't live in those regions anymore. Unless, of course, we've got air conditioning, but that has all sorts of other implications. So this becomes pretty important. How do we reduce this heating of the atmosphere? And of course, one way we can do that is through the third step in the water cycle, and that's looking at, well, what is causing this increased concentration and how can we actually reduce it, basically to lower that warming effect. And the increased water in the air is due to, as we said before, these aerosols, and we've been increasing these aerosols dangerously. So we've been putting about 3 billion tons a year of extra dust into the atmosphere because we've aridified 5 billion hectares of the Earth's land surface so that it is now basically desert and wasteland, and massive quantities of dust are getting eroded, and that dust is forming these aerosols. We're also burning about 350 million.
Whoops. Seemed like there was a pause there. No, Walter's frozen.
Yeah.
Sorry, buddy. The pause.
There we are.
All
You're
right,
back, Walter.
Sorry, there was a momentary freezing. Yeah, you dropped out for maybe 30,
Okay, well, look, we can pick
seconds.
up anything in the Q&A at the end that's missing.
All right.
Okay, and we're also burning about 2 billion hectares a year of grasslands and crop stubbles. And again, that's adding enormously to those aerosol loads. And of course, on top of that, we're also burning about 8 billion tons of carbon every year in our fossil fuel use. So we are massively increasing the load of those aerosols. And so now if you go from basically, the Middle East, the Eastern Mediterranean, right through to China, we have what we call the Asian brown haze, a toxic pollutant brown haze of these aerosols, these humid airflow, sitting about 4,000 meters above that whole land surface, heating it and aridifying it. And that's enormously, destructive of the biosystems and, of course, dangerous for human health. And we've got to change that. And as we're saying, we've got to change that by removing the source of these aerosols. So basically by land cover, revegetation, so we stop the dust, we stop the burning, and of course we stop these particulate pollutants. So there's again a key area where we, through land management, influence these aerosols, and that influences the amount of water in the air, which influences the climate. So in each of these cases we talk to, there's very simple, natural and effective ways that we, through land management, can influence it, but we've got to understand the connections to be able to do that. Okay, the next part of the water cycle that we want to talk about is actually really quite significant to the climate, because as we've talked about, the climate is regulated by the greenhouse effect, but there's 3 factors really that drive the greenhouse effect. And we've only ever, in science and in politics in the last 30 years, really looked at one of them, which is, in a sense, the CO2 concentration. But in fact, the dominant driver of the greenhouse effect isn't the CO2 concentration, but it's the amount of energy that's being re-radiated from the Earth's surface back into the air, which drives the greenhouse effect. It's a bit like a stove, isn't it? It's a case of, yes, the CO2 might be the pan on the stove that can absorb the heat, but it's the actual re-radiation from the Earth that is basically governs how high we've got that stove turned up. Okay, now basically how hot the Earth gets governs how much re-radiation is given. That's simple physics, the Stephan-Boltzmann equation, and basically what's important about this is the amount of re-radiation from the Earth's surface is the 4th power of the temperature of that surface. Now, for those who aren't into mathematics or physics, this is profound because the effect just goes up exponentially to the 4th power in degrees Kelvin. So it's temperature times temperature times temperature times temperature. So you can see very much that a surface that is 20 degrees centigrade gives far, far, far less re-radiation than a surface that might be 60 degrees centigrade. Okay, and this is of course exactly what we've done when we've aridified and degraded our land surfaces. Because if we have a moist, cool, protected land surface, well managed, it rarely gets above 20 degrees centigrade, even if we've got a 35 degrees centigrade day in the air or temperature in the air. Okay, rarely gets above 20 degrees. Mostly it's sort of 18, 15, 18 because of that cooling effect from the water evaporation. But if we degrade that land surface, if we clear that land surface, if we expose it and basically expose it to that incident solar radiation, it will easily heat up to 60 degrees plus centigrade. And we know that like asphalt and concrete and, soil surfaces exposed. And so these exposed heated surfaces massively increase the re-radiation infrared. And this infrared radiation, the quantity is actually how high we've got the stove turned up. So in simplistic terms here, yes, we can change the CO2 concentration, we can change the water vapor concentration that absorbs the heat. But now if we think about it, the reality is we've got this far, far more powerful opportunity to turn down the greenhouse effect, to simply turn down the greenhouse effect by protecting our soil surfaces and stopping them heating up to the 60 degrees and keeping them at that natural 20 degrees or below. Okay, so this is really profound because quite frankly, we're not going to be able to solve our climate crisis just by reducing CO2 emissions. Okay, it's going to take centuries before we can actually bring that carbon level back down to the 350 parts per million or lower that scientists are telling us we need to. We're not going to bring it down because the oceans contain 50 times more CO2 dissolved than the atmosphere. And as we draw down carbon from the air, even if we tried that, and we're not even doing that yet, but even when we do, the oceans will re-equilibrate carbon dioxide back into the air because it's been acting as this massive global buffer. Secondly, as the oceans warm and acidify, they're going to be releasing more CO2 anyway. So we're not going to get CO2 down in a hurry. It'll take centuries of work. It's not a problem, but we do have to control the greenhouse effect and what we've been talking about by actually turning down the infrared re-radiation, turning down the stove. We can actually do that at a power of 10 to 1 compared to playing around with the CO2. No questions, we also have to reduce CO2. We also have to draw down. We've got strategies to draw down 20 billion tons of carbon per annum from the air back into the soils, but we're doing that to rebuild the soil carbon sponge, not just to reduce CO2, because that by itself isn't going to cool the planet. Okay, so really quite profoundly, we have this tool, we have this capability through land management to actually reduce the greenhouse effect but also through that land management, reduce the amount of dust and particulates going into the air that create the humid hazes which warm the planet. So we've got a double capacity to actually regulate and cool through these land management and hydrological processes. It gets better than that though, right? So now we go into the next step in the hydrological cycle. We say we've got all these humid air hazes in the air. The issue is, how do we get them out of the air? You know, how do we turn them from a haze, which is warming the planet, into something more productive? And that's very simple. Nature does it all the time. It turns humid hazes, warming humid hazes, into cooling clouds. And it does that very simply by just coalescing these haze micro droplets, taking 1 million of these micro droplets and turning them into cloud droplets, a larger cloud droplet. And those cloud droplets, of course, then coagulate or come together as clouds. And those clouds have got an enormous albedo reflective effect, re-radiating or reflecting incident solar radiation back out to space. Okay, wonderful picture of clouds. It's a good rain cloud. We'll come into that rain cloud. But basically, you know, when a cloud comes over, it can get 10, 15, 20 degrees centigrade cooler on the surface almost instantly, because instead of that incident solar radiation reaching the Earth now, it's being re-radiated back out to space. Okay, we talked about it, 342 watts coming into the Earth on average all the time. These clouds regularly re-radiate 120 plus watts per square meter back out to space. Okay, so on average, 1/3 of the heat that used to come into the Earth basically was reflected back out to space by clouds. Naturally, previously, clouds covered 50% of this planet at any one time. So half the Earth was, in a sense, blanketed by clouds with a cooling hydrological buffering effect. Of course, we've reduced the level of those clouds because we're keeping more of them as warming humid hazes. And of course, what we've got to do is, as in nature, put more of those humid hazes back into clouds. And we can do this very, very simply and naturally and safely. And of course, just as nature does, there are 3 processes that do this. And it's all basically comes down to coalescing these haze droplets into cloud droplets hygroscopically. Okay, that's a big word for suction. So sucking these little haze droplets into larger droplets, and these larger droplets becoming then reflective. Ice crystals, salt crystals, and certain bacteria are the most critical and effective, I mean, the only means that we can do this, or nature does this. We can't do better than nature. So it's really the nucleation of hazes and their coalescence hygroscopically into these larger droplets that creates the clouds. And so all the work we did in the 1950s, 60s, and subsequently on cloud seeding was always involved with how do we actually manage either the ice crystals, the salts. Much less work has been done on the microbial, bacterial nucleation, but how do we actually sort of use them? And of course, we use dry ice and silver iodide to do this whole cloud seeding work. And it works, and it's been very effective, but basically not extensively used. But whereas we can play around with ice, dry ice and silver iodide, nature basically doesn't have aeroplanes. It doesn't need aeroplanes because it does it naturally. And in tropical inland region, it does most of this through these bacterial precipitation nuclei. Okay, and these nuclei again sort of bring in, okay, beautiful cloud forests. These nuclei are actually generated by forests, which then transpire these nuclei up into the atmosphere, and these nuclei are now coalescing hazes into clouds. Actually, the next step I'll talk about into rain. And of course, that creates the hydrological cycle. So rain is a bit controversial, but absolutely true in nature. Rain is a symbiotic function of those forests, right? The forests are symbiotically, through these microbial processes, generating their own rainfall. So the Amazon is basically getting 3-4 times more rain than it would otherwise, because every day these forests are generating these nuclei, coalescing these hazes, causing more rain. You can set your watch on at 4 o'clock every afternoon in a tropical rainforest. You'll get that thunderstorm, and that water cycle every day is being nucleated and driven and cooling that planet. These rainforests rarely get above 35 degrees, 30 degrees centigrade, because of these hydrological constant daily cooling cycles. Okay, so it's restoring that formation of these dense reflective clouds, cooling clouds, and rainfall that is critical. And actually that sort of, in a sense, comes back to the full cycle, because we started off with the small water cycle, we started off with transpiration, but of course transpiration can't happen unless the soil has water. Okay, so this really gets to the guts of it, because it's really restoring the Earth's soil carbon sponge and its capacity to hold water that is really the cardinal point whereby we can rebuild these water cycles. Because without that sponge, without that capacity to store water, we won't have the transpiration, we'll have all the dust, we'll have all the higher infrared reflection, greenhouse effect. Okay, so we need to have that sponge to restore these water cycles, but also to infiltrate and retain the rain that we can form through these nucleation processes. So in a sense, we had that diagram of the water cycle in the beginning, and so we've taken a fairly quick and hopefully not too complex journey through the processes that govern that, and really to highlighting where we humans, through wise land management, can actually influence it, each of these stages, to restore it, regenerate it, cool it, and in cooling it and hydrating our landscape, address the water, the food, the habitat, the social stability imperatives that are facing us. It gets a little bit better than that, though, because once we've got that cycle, we've got other factors coming in. See, by taking that humidity out of the air through this cloud and then rainfall nucleation, we actually create what we call, in common language, radiation windows, nighttime radiation windows. We open these windows. So if you ever lived in tropical environments, you'll get this thunderstorm late in the afternoon, early evening, and you'll notice, and everybody's always written poems about it, then you can see the stars, because the water for that short period has been moved out of the air. And because the water's been moved out of the air, you've got the capacity for, again, heat from the Earth to directly re-radiate back out to space, cooling that surface, sorry. And so, again, very, very powerful cooling effect through removing the humid air out of the humid aerosols out of the air through that rain and allowing that re-radiation. And this is, again, critical, because 60% of the warming that we're, in a sense, suffering as global warming is due to increases in nighttime minimum temperatures, because the planet can no longer cool itself at nighttime as it used to do, because we've got these persistent humid hazes. Okay, so it's really quite significant. It's the removal of that humid haze through those rains that then reopen those radiation windows and help cool that planet. And again, it can be 30, 40 watts per square meter of cooling that comes as a consequence. There's another very powerful consequence of this rain, which is really very, very critical as well. When we condense and nucleate this rain and the rain falls to the earth, we create actually an area which had been very high pressure air because it had all these water vapor molecules at enormous heat. We create this we take this high pressure zone and we actually create low pressure because we've removed all that water and all the energy in that water. So we've created a low pressure thing. And so instead of having a high pressure heat dome over continents, particularly arid areas, we create low pressure areas. And it's just logical physically that basically, yes, low pressure, warm, wet marine air can only flow into low pressure areas. It can't, low pressure can't flow into high pressure and displace high pressure heat domes. And so we end up with what we call the biotic pump, okay, a process whereby basically rain, humid air flows inland into low pressure areas, but in a sense can't flow into high pressure areas. And so this drives many of the monsoonal effects that we actually have on the planet. And of course, those monsoons are critical for keeping, some 4 billion people with reliable water, food, habitat, and futures. And we can see this particularly powerfully in the Amazon, where these biotic pump effects are bringing water constantly from the Atlantic into the Amazon, keeping the Amazon green, hydrated, and productive. If those biotic effects ceased, the Amazon would go back to a dryland savanna at best, or aridify at worst. And of course, in Australia, we've got exactly the same situation. Up to about 8,000 years ago, we had an Australian monsoon. Okay, we had basically humid air coming into every summer and basically going right into central Australia. Lake Eyre was a 25-metre deep freshwater lake. It's a lake, actually, for those you don't know, in the middle of Australia, now a salt pan, but it used to be a freshwater lake up to 6,000 years ago. And basically, it was because we had an Australian monsoon, because this biotic pump effect brought water from the Indian Ocean every summer into Australia. The indigenous people in Australia understood this. This is part of their stormwater dreaming understanding. They didn't use physics as we describe it, but they had a very, very sophisticated understanding of these dynamic processes, but also how their land management affected them. And so the elders had this responsibility of stormwater dreaming. How do we manage land to keep this rainfall, monsoonal effect going? The rainbow serpent, which is a key cornerstone of Australian Aboriginal mythology, is all about that monsoonal induction and keeping the rainbow serpent happy so that that rainfall, that monsoon, happens regularly. Okay, so basically we've talked about the water cycle. We've sort of said, look, here are some powerful effects like these biotic pumps. But really, just to conclude, I wanted to just come back to now talking about, well, what is it that we can do about it? And as we said in the beginning, what we can and have to do about it is to actually rebuild the Earth's soil carbon sponge. Okay, we've got to draw down carbon from the air and put it back into soils, because only by rebuilding the sponge can we restore this water dynamics and cooling dynamics. Okay, so, and that's very powerful because we can do that simply and naturally, simply by smart agriculture, growing plants, and making sure a significant part of the biomass those plants produce through photosynthesis gets biosequestered into soils through microbial carbon fixation to build the sponge, to build the hydrology, to rebuild these healthy ecosystems. Healthy Soils Australia is working and has worked for 15 years, a whole lot of different projects, grassroots with groups of farmers. Now we're working actually with internationally also with groups to really say, how do we actually accelerate and extend this practical drawdown of carbon? We were in the UN last May, and here's papers to say, look, we can practically, profitably draw down 20 billion tons of carbon every year. That's twice our fossil fuels or current net emissions, but we can draw this down into our soils to rebuild the sponge, to rebuild this hydrology, to rebuild this cooling. And it can be done, but only done through community, grassroots, farmer, direct action. It's not going to happen through politics. I mean, obviously we need politics, we need to address it, but the leader has to be grassroots sort of action. So carbon, instead of being seen as a pollutant or a bad guy, it's really the building block. We've got to take carbon from the air back into our soil. Charles Keeling for the last 50 years has shown us that yes, we are increasing that carbon in the air. It's a symptom of our land degradation. The challenge is to reverse that degradation, take that carbon from the air, build the sponge, rebuild the hydrology. When we do, we can actually change all these elements of the hydrological cycle to have a cool, safe, natural planet. So look, that's the picture. It's all doable. It's exactly how nature for 3.8 billion years has regulated this sort of planet, and it's exactly what we can do to help nature re-establish, re-accelerate those processes. So it's that's simple in a nutshell, but it's also, I suppose, it's got its complications. But really, over to, I suppose, now having a discussion about, any point of detail, but also where do we go and how do we empower communities and peoples and actions to make that happen. So thank you very much, Neil, and thank you, Raleigh, and then let's get into the discussion, right?
Right. So what I want to do is I want to take 15 minutes and walk you through a case study that I am intimately involved in. It's the work I've been doing for the last 7 years, because you've given us a very big picture, and there's a lot of ways people could run with this, and potentially the wrong way and potentially the right way. So I kind of want to run some of this stuff by you as a test against what some of these assumptions are. And I'm going to share my screen, folks, and take 15 minutes just to walk you a bit through what I've done, because what Walter's been talking about is half of the thrust of the work that I do in Saudi Arabia. So let's, Raleigh, let's switch to my screen.
You got it. I'll make you the presenter. Okay.
Because I've got some stuff ready. Yeah, here we go. So Raleigh, can you let me know verbally when you see my screen, because I won't be able to see everyone's comment.
I can see your screen. How about everybody else? Can you see Neil's screen? Give me some ones if you can see it. Just type in the chat box below 111. Hey Tim, yeah, we'll get to the questions right after, but I know you guys are itching with some good questions. This is so awesome. We got Judy Schwartz on here, Brock Dolman, Tim. We got a lot of folks we know. We got some really cool people on here.
So Walter, where I am is just south of Mecca in Saudi Arabia, right? About 50 kilometers south. And since the 1950s, this region has seen a lot of desertification due to a loss of the traditional land management system. There was a tribal management system called the Himma that was pretty much made illegal in the 1950s. And since then, the tribal boundaries have mostly broken down and anyone can graze anything at any time. And the people that I work with belong primarily to two tribes in the region of this yellow dot, this yellow place mark on the map. And because of that desertification and because of a growth in population. They can't feed their animals on their land anymore. So they need to purchase imported alfalfa and straw from Australia. Actually, we're buying Australian alfalfa in Saudi Arabia. And to get the money to do that, they're chopping down the trees in their region.
Yeah,
right?
sad. Mm-hmm.
So they're chopping down the trees to be sold as firewood, taking that cash to buy imported straw, and in the meantime, their land base is completely desertifying, and we're about 70 years into that process. Okay. So what I've been doing is working with these tribes on a prototype where we have been managing the watershed on a very small site, but we have the whole watershed where we've got the mountains, the flood valleys, and the floodplain. And our strategy has been to essentially manage the water so that we can restore a savanna type ecology to this site and have that savanna double as an agroforestry system, right? So it's got the environmental sustainability to it and the economics from the produce off of the agroforestry and off of restored grazing. Okay. I'll show you folks just a couple before and afters. This is what it looked like 2 years ago. You can see there's a lot of earthworks in there, a lot of trees that we've planted, some terracing compared to that, which is in 2010. Here's some closer up stuff. This is looking west, and this is February of 2011. This is 4 years later. This is a ditch on contour that harvests water from the flash floods. That's 2012. That's 2015 on the same place. All right, so there's the stuff that's local, where we've seen an increase in biodiversity. We're seeing an increase in soil carbon, because obviously, like you look at my before shots, there's literally zero soil life and soil carbon here, right? And so we've gone from zero in this picture to, there's something here, right?
Excellent. Excellent. It's a journey, and excellent. Look, we'll talk about it. Yep.
Okay, so we've gone from nothing to something, right? I can't tell you if it's 0.5% or 1% soil carbon, but the entire region has this whole. By the way, is my control panel on your screen? Are all of you seeing that as well?
Yes.
No, you're good.
Okay. So we have the Red Sea on our west, and we have these mountains on our east. So we have a maritime effect on our west side and an orographic effect on our east side. So we're nearly in what I would call a closed loop hydrology, where so you've got the Red Sea in the middle of that, and you've got that mountain range of solid blue just to the east of it, where
yes.
all of the water in our air comes from the Red Sea.
Yes.
It hits those mountains and we get an orographic effect, and then it floods right back down into the Red Sea, right? So we're in a closed loop hydrology. And so what we have, from what I have been able to surmise, Walter, is that through the desertification, there's been an increase in dust.
Yes.
And a decrease in all of the effects that comes from having foliage on the ground.
Yes.
Right? My understanding is that dust in a desert is a precipitation inhibitor.
Yes.
Right? Whereas
because it's
it's the wrong type of nuclei to be cloud
Absolutely.
condensation nuclei. Whereas that dust, if it were, say, over Washington State, it would be inducing rainfall, but in a desert, it's inhibiting it, right? Because they've found dust from the Gobi Desert all the way over in Vancouver, where it's it can be a major contributor to the rainy conditions they have there. But in the desert itself, it's inhibiting that rainfall.
Can I step in there just briefly?
Yeah.
Yeah, look, that's so important that you mentioned that, Neil. Look, there are two sorts of nuclei in this game. Nature always works in balances. There are those haze nuclei, things like dust, right? And they create hazes. And that doesn't create rain, that aridifies, because those hazes are persistent. They can't coalesce, they're negatively charged, and so they repel each other and they stay there as persistent hazes. And they aridify and desiccate. The other nuclei at the other end, the cloud condensation nuclei and the rain nuclei, they're hygroscopic precipitation nuclei, and they are completely different. And so nature works between hazes and clouds, right? And they're two separate nuclei classes. And definitely you don't have those precipitation nuclei unless you've got that vegetation, you've got that cooling effect, because you're not going to get ice crystals there, right? You'll get some salt. And so definitely right. So there's two classes of nuclei with completely different rainfall effects. Certainly you'll get Gobi dust coming down in Vancouver, but they haven't nucleated that rain in Vancouver. In Vancouver, it would have been salts and ice crystals and some of these aerobacters.
But it's also much colder there, isn't it? Isn't temperature a major factor there, where dust nuclei can be cloud condensation nuclei if it's cold enough, or am I wrong?
No, dust does not condense ever, doesn't condense rain. Basically, three things can make rain: ice crystals, salt crystals, and these bacteria, right? But
Got it.
Dust is far too small, and it just creates the hazes. Now, sure, the dust will come down from the haze. You know, there'll be dust particles in the haze. So when you get a raindrop, which is about 10 million haze micro droplets, it will have 10 million dust nuclei as part of that raindrop because it's captured those hazes.
Right.
But those dust that have not nucleated that rain.
Okay.
Only it's a biological process largely. I mean, obviously the ice up in high latitudes, but basically the dust won't do it.
Got it. So here's my thinking on this, Walter. We have managed to multiply the foliage on our small prototype site by over 100 times, right? We had about 100 trees living on site before, and now we've got about 5,000.
Right.
And what I perceive, and this is my graphic, obviously, but what I expect will happen is on that small site, we should be reducing dust because we've got the foliage cover, right?
Yes.
The trees break the wind, the forbs and the grasses will add some structure and prevent that wind from picking up all the dust. And we should actually be capturing dust in lower winds as it runs through our agroforestry system, right? So we're reducing dust. At the same time, we've got the evapotranspiration off of this stuff, which is quite low because they are desert trees, but there's still evapotranspiration happening. So there's going to be an increase in water vapor, as well as those aerosols and those VOCs and that CCM that comes off of the trees.
Yes.
Right?
I put money on it that basically if you continue with what you're doing, you will find that basically you will be transpiring, you will be putting more of these, microbial nuclei, but also you'll be creating that low pressure moisture area, and the rainfall will intensify on your revegetated site relative to control sites 20 kilometers along the range, which is still desert, right? So rain follows rain, rain follows vegetation. You can actually reinforce relative to the rest of the coastline the moisture capture on your site. Right. The other thing, Neil, that's so important, and this is so important, we scientists have been measuring rain for 500 years in little tin cans that we call rain gauges, right?
Yep.
But rain gauges only work in European context. In these desert environments, 80% of our rain is often in fog, mist, condensation on vegetation surfaces. So the way we measure rainfall is giving us a massive misleading underestimation of how much moisture these these vegetated areas actually harvest.
Okay, so let me get you to the final step of what I've been talking about. The entire west coast of Saudi Arabia has these flood drought systems. Right now you're looking at a 10 million acre spot where west is down and north is to the left, where we have these mountains. The rainfall happens in the mountains, you get these massive floods where you'll lose between 40 and 80% of the water of the rainfall directly to the Red Sea because we have such a short floodplain.
Yep.
Right? If we were to manage those floods such that that water was going into the ground, there's enough water in those floods, even if they're happening every 4 or 5 years, to convert this whole place back into a savanna.
Totally agree.
Right?
Totally agree.
Back into, so we're moving from a desert ecology to a savanna ecology. It's a different stable state.
Totally agree.
And what should happen if we were to do that is we will get rain more frequently, and we should be getting more on average per year. Would you agree with that conclusion?
Yes, and yes, absolutely. And also what I'm saying is half of the moisture may not be in the form of rain, but will be in nighttime condensation on those vegetative surfaces. We can measure that, and it'll blow your rain gauge data significantly, right?
Right.
And yes, compared to, absolutely. And what you're doing there about, here's a vegetation, it's really grazing management. It's really looking at how do we allow that pioneer vegetation to reestablish rather than being grazed immediately. And then, as in nature, you can accelerate that regeneration. Saudi Arabia, Oman, they were actually green belts, 2,000-3,000 years ago. Much more productive before this overgrazing and degradation. So,
and the net effect of this would be to cool, even though we're moving from, because the albedo question to me is tricky, because the sand is, light yellow, whereas we'd be moving to a very, a much greener, a much darker kind of soil profile and foliage profile. So the albedo changes there, the specific changes, the radiance changes, and so there are so many factors here.
Yep. Right? But again, the albedo is a bit of a misnomer there because, look, if the leaves are they can be dark because they're using the energy to evaporate and transpire the water. So there's no detriment to the leaves to being dark, right? They really need to absorb energy, albedo, to have the energy to transpire, right? And so it's not a negative for vegetation to be dark because it's cooling through these latent heat fluxes through this transpiration.
Right.
So do you understand? Even if you've got a darker vegetation compared to the sand, you're still ahead in terms of the overall heat dynamics. It's just
because
that your transpiration is offsetting the albedo effect.
Yeah. All right. That's my case study for you. I ran this by Professor Milan, who worked with the UN on modeling agriculture's effects on hydrology. I wanted to run it by you as well as by our audience to show what the applications of this potentially are. I mean, I'm saying we can convert 30 million acres of desert into a savanna.
Absolutely.
With the accompanying economic and environmental impacts of that.
Absolutely. Look, we went to the UN Global Soils Week 2015. We've got a Regenerate Australia, we call it a project, 300 million hectares of northern inland Australia. And it's the same thing. If we manage fires, if we manage grazing ecologies, we restore that soil cover, the vegetation cover, we rebuild the sponge, we can do exactly that. In your case, it's actually excellent because you've got wonderful control sites adjacent where you can show the difference. You could say that this valley revegetated is now totally changing compared to an equivalent valley 20 kilometers up the range.
Absolutely.
Where it's still desert. And all I'm just saying, you can accelerate it way beyond the status quo through this water harvesting by vegetation, not just the rain gauges, right?
Right.
I mean, we'll talk about later, but there's very elegant, very simple ways where we can say, yes, both substantiate that evidence, but also then accelerate that hydrological capture.
Absolutely. Okay, that's all right, folks. That's Walter's presentation. I'm injecting myself into it because I think what I'm doing is highly relevant, and since it's my webinar, I'm going to take my prerogative and ask my questions first.
Thank you very much.
We want to open this up to the rest of you. If you've got questions for Walter, if you've got questions for me, we can bring them up in any other webinar that we do. But I'm going to be around for a while anyway. But we had some really good ones earlier on in your presentation. Folks, can you type those back in, and we'll get to your questions now. We've still got a good 25-30 minutes.
Yeah,
All right.
pop those questions in. If you actually, if I replied to your question and said, hey, ask during the Q&A, just copy that and paste it back in. We're going to circle back to it. Okay, so the first one I saw was from Imogen. Imogen's asking, how do you capture floodwaters and keep them in the ground? Plant stems?
Okay, look, floodwaters, yes, you capture floodwaters by the sponge, right? It's a very simple thing. There's a rain drop falls on the soil, and basically where it falls, the objective is to get that raindrop into that soil, into the sponge, and then to rebuild the in-soil reservoirs under that whole landscape. We only have a flood if we don't have that, if we've got hard capped, erosive surfaces that then don't let the water infiltrate, go into the creeks, we have a flood. So the whole point of once you have a flood, the answer is, hey, we are missing that water. We're losing that water. We don't want to lose that water. You build the in-soil reservoirs, you build the sponge, and you do that by saying, okay, just as Neil has shown us, okay, how do we restore the grassland covers on that area? How do we create shelterwood vegetation that breaks up, and adds more carbon into that soil? By rebuilding the sponge, we can hold that water where it falls so we avoid the flood. Now, once we have a flood, sure, then there's a whole lot of in-stream structures. In North America, you had 400 million beavers doing that before white man came. Fantastic, flood, water storage, leaky weirs, capture. We've got people in Australia, Peter Andrews, for example, who've advocating same, in-stream restoration structures. There's a whole lot of work on that. But really, the bottom line is if we can keep that water directly going into the soil, we avoid the floods. So, I'm not saying that, floods, you've got to do something about floods, but really starting at the front of the pipe, avoiding them, rather than saying, how do I manage a flood at the end of the pipe? But yeah, that's my answer.
Awesome. So here's a kind of a few-part question from Ron. So he's asking about the time frame that we could conceivably actually draw down, the carbon and actually reach a safe level. So his question is, do you all believe that the world and Australia's most valuable asset is to preserve the land by reinstalling the natural intelligence of the landscape? If 30% of the world's agriculture was to convert to mulch farming methodology incorporating the NSF system and only 15 tons of organic matter were used per acre, this would draw down enough carbon to have pre-industrial levels in the atmosphere within 10 years. That wasn't really phrased as a question. A question that I did get was, okay, can this conceivably be done in a 10-year time frame? Like, what would it require on a global scale to do this within a 10 to 15 year time horizon?
There's a wonderful Chinese proverb which says, you know, when is the best time to plant a tree? And they say 20 years ago. And when is the second best time? It's now. And of course, yes, can we do it in 10 years? And I'm not saying the whole world will fall off the cliff just in 10 years, but it's intensifying, getting more extremes. But the good news is very simple. We work with very innovative farmers all over Australia. There's other people, Peter Donovan and people in the States, really working with innovative farmers. And these innovators are showing that, yes, we can, right? Even a couple of years of restoration farming, basically, you know, keep managing those grasslands, managing shelter woods, getting the carbon into the soil. Within 2, 3, 4 years, they're starting to have effects on soil structure, infiltration, retention, and all of these have positive feedback multiplier effects on productivity, resilience, and more growth. So basically, the answer is yes, we have to do it. Yes, within 3 to 5 years, you're getting positive effects from all these case studies. We have farmers, you know, within 10, 15 years are putting 10 tons of carbon per hectare per annum back into their soils. Another example, if you look at the Dutch, you know, like they take stinking saline sediment soils from the bottom of the Rhine, you know, the sludge from the bottom of the Rhine Valley, and they turn it into polder soils, some of the most productive, you know, biodiverse soils, again, within 10 years. Okay, so yes, we can. Obviously, you've got to look at your particular soil and you say, okay, how do I accelerate these regeneration processes? How do we use nature? How do we help nature do that? Don't beat yourself up if you're not doing 10 tons, if you're only doing 3 tons, because 3 tons is better than the -2 tons that our conventional agriculture is still oxidizing out of soils, right? So what I'm getting at is it's a bit like empowering people everywhere, doing it as smartly and as quickly as we can. And the answer is nature has given us the tools. The case studies are there. I think it's fair comment to say that this is where these regional mentored groups, you know, regional groups, we're saying, okay, what's the experience in this landscape? How do I work with others doing it? How do I share knowledge and experience? That's all part of that acceleration regeneration process.
Awesome. Thanks for answering that. Next question's from Tim. Tim Sexauer asks, to be clear, would you say multi-layered plant cover is not just an essential part of the soil sponge, but key to restoring the water cycle because of its nucleation functions?
Okay. Thanks, Tim. I mean, simple answer. I'll try to give a simple answer. It's a complex question. Okay, first of all, multi-story is absolutely important. Why? Because just as we've got a multi-dynamic above the ground, we've got to recreate that multi-species dynamic integration, that interface of the mineral soil with the microbial and the root systems going down meters, right? I mean, our desert environments, coming back to Neil's stuff, we've got spin effects with roots down to 50 meters, right? So it's using that whole, anchoring that whole soil environment, using water through that whole soil, in-soil reservoir environment. So multi-species, absolutely critical, because we're going to bring that whole mineral ecology back into that biological cycle, and we can do that through multi-species. If we're smart, they don't compete with each other, they're synergies, they cross-reinforce each other. So agroforestry, shelter woods, you know, like actually they help the actually plants growing below because of these synergies. In terms of the nucleation, this is an area which is, in a sense, there's an enormous amount of evidence in the ground, on the field, but scientifically we don't have all the answers, right? So the question is, what species of trees, at what age, at what sort of stage of development, et cetera, are most effective at this nucleation? We've measured we know what's happening up in the atmosphere. The atmospherics atmospheric physics is pretty well worked out, but this business about what trees at what density, age, etc., give us the best nucleation, that work's never been done. We have a lot of evidence where we've cleared forest and destroyed these forests, then the rainfall has crashed because of this crash of this nucleation cycle. For example, in Western Australia, we have a thing called the rabbit-proof fence, and we cleared all the land to the west, which was moister for wheat farming, okay, because it was more productive land, and we left land to the east of this rabbit-proof fence as just woodland. And of course, 40 years later, what has happened? The woodland that was previously drier now gets 20% more rainfall than the cleared land. And of course, everyone is complaining that they were diddled, and then other people are speculating, does a barbed wire fence create rain? That's not true either. But the point is that, you know, we've got evidence, but the actual, you know, what number of trees, at what age, at what density are optimizing this biological bacterial harvesting or nucleation of rain, we don't have all the specifics. And in a sense, we're in the front line, as Neil has explained, as Neil is doing. How do we actually pioneer these areas, document them, and put that evidence into the record?
Awesome. Thanks for that, Walter. Next one is from Mark. He says, what is thought to have broken the Australian monsoon system 8,000 years ago?
Okay, again, thank you, very prescient, like wonderful. Okay, now this is very not contentious. I mean, but again, we don't know because we're here now. We weren't there watching it. Basically, the whole of Northern Australia was in a sense a savanna with gallery rainforest in the riparian areas. And it was much, as we've talked about in the Amazon stuff, it was much more greener, mesic, cooler. Okay. And what's happened is that basically over the last 6,000 years, it's got drier and drier. And now, of course, it has this high pressure heat dome over it mostly. And the monsoon still comes every year, but it's more to the north and it doesn't extend as far south. So the whole stormwater dreaming of the indigenous people was about, well, what's going on and how do I do the right thing by climate and nature to, you know, keep that monsoon coming? And what we understand has happened, actually, it's quite significant, and comes back to what Neil was saying. Previously, we had a savanna and we had megafauna. We had massive, big herbivores, and these guys browsed that savanna flora and the shrubs and the trees, turned it back into soil carbon, and maintained a very active soil, hydrology and carbon cycle. And basically, when those megafauna disappeared, over that period, and basically the last evidence is, 5,000, 8,000 years ago, roughly. When that megafauna disappeared, then of course we didn't have these herbivores eating this vegetation, right, and cycling it. And we built up a massive fuel load. And of course that fuel load would then burn. And of course when it burnt and oxidized, it basically completely, degraded that vegetation and moved it back towards desert. But because of those fires also barbecued the Aborigines, literally, right? Because, the fires in Australia, you can't survive them, broadacre fires. So the Aborigines very, very quickly and very intelligently had to learn fire stick farming and managing the fuel loads through control burning, regular control, mosaic, cool burning. And so then we've basically created a new ecology where we had basically, this fire stick farming, mosaic, cool burning, managing the fuel, but the whole system was still, in a sense, oxidizing and degrading compared to what it had been previously. And so I think we've got this balance between, here is avoiding the big hot wildfires, but in doing so, we're still, through the control burn, still oxidizing. And now the question is, can we reintroduce ecological grazing systems that replace what those megafauna, those previous marsupial browsers were doing? And if we can we actually reduce the fire level and therefore build the soil carbon, rehydrate those environments, and as Neil has told us in Saudi Arabia, progressively rebuild that moist environment and therefore extend the monsoon back into Central Australia to rehydrate and cool it. So that's our understanding of what's happened. That's our sort of vision of where we could go down the track. But basically, yeah, that's where we're at. It's using nature. How do we work with it? How do we rebuild it? But it's not a done deal. We haven't, it's still an arid environment at the moment. But if we look at all the archaeological evidence, I mean, Central Australia, the ranges there were the real key to the whole monsoon. There were still old river systems, massive river systems, 8 massive river systems coming from those Central Australian ranges. And yeah, within 8,000, 6,000 years ago, they were still active.
Man, I gotta say, Walter, thank you for blowing my mind 100 times over. This is, I was just in awe this whole time.
Neil. No, sorry, Riley, your mind's important because we need you doing all this work and keeping this going, right? So I don't want to blow your mind.
Yeah, no, it's absorbing.
But look, on that front, look, see this, I mean, okay, we have to be audacious, right? We have to be audacious because really, this is how, I mean, we've got to read this land. We've got to read the thing. What happened? Neil raised it with Saudi Arabia. Yes, it was a different environment. When people left Africa, they went through Oman, Saudi Arabia. It was still all green. All the records show it was green, like it was grazing, all that. So what have we done to it? And then it's, what do we do to restore it? Okay, it's not hard. It takes time, but we can do it.
Awesome. So I know we're probably gonna end this pretty short. It really depends, Walter, however long you want to stay here. If you got to get going, we respect the heck out of your time.
No, we'll keep on asking the questions, and then yeah, when we run out of juice, we run out of juice, right?
All right, fantastic. We got it. Well, there's definitely plenty. Here's one by Tom. He's saying this is about the oceans. He's asking, is there anything we can do to the ocean to assist the water cycle?
Well, yeah, 71% of this planet is covered by oceans, average depth of 4,000 meters, right? So obviously a massive quantity of water is evaporated from the oceans and then basically comes onto land. And as the previous question said, yeah, then it all floods off. And of course, the answer is no, we need to keep that water coming from the oceans. We need to keep it on the land. Actually, this is very important. And Marco Kravchuk mentions that sea level rise can be moderated significantly by retaining more water in that soil, carbon, sponge, and in-soil reservoir. I mean, if you think of it, we've got 2 meters of biological soil across, the 13.9 billion hectares of land on this planet. And if we're putting a meter of water in that soil because of the sponge effect, we can actually massively reduce sea level rise and actually give us some time to rebuild some of those systems. So yes, so that's the point of hydrology. I mean, basically the oceans are, well, just such a big, powerful buffer in the Earth's climate. So we just have to respect them. I don't know if we're going to change them. There are things though that we can do to the oceans, which is very important, and it's just profound. Before, about 200, 300 years ago, we had massive numbers of whales and, these mammals in the oceans. And we've now found out that these massive numbers of whales, they of course defecated in the oceans, clearly, but that was basically the nutrient source to drive all the phytoplankton or most of the phytoplankton in the oceans, right? So it was really, it comes back to land too. It's the actual herbivores grazing the oceans that can turn them again from a biological desert into a much, much more productive carbon drawdown system. And the keystone species were doing that were the whales and their defecation. And out of that, you had all the, the blue-green algae and all the phytoplankton growing. Out of the phytoplankton, you had the whole food chain growing. And so this whole crash in ocean ecology, ocean, life, fish, is really driven by us crashing this keystone species through whaling, the last 200 years. And the question is, can we rebuild, for example, whale populations? And when we do, as a keystone species, what multiplier effects do they have? And of course, massively increase bioproductivity, carbon drawdown, and really have an enormous contribution globally to the biosphere.
Man, great answer. Okay. So Mary's question, her context is she's in an area with a lot of forest fires. Mary, I'm trying to remember. Okay, she's in northern Idaho in the States. Right. She's asking, is smoke from forest fires the type of aerosol that condenses rain or that stops the condensation? So her question is, she says her project is aimed at reducing the production of fuel available to forest fires by using animal systems, and she wants to decrease that fire feedback loop.
Yeah, no, good. And critical, as I mentioned, so many times, on average, 350 million hectares every year is burnt forest, and there's an additional about 2 billion hectares of grassland burnt every year, right? Massive. And of course, a lot of this carbon goes up, obviously, as CO2, but also a lot of particulates and smoke. That smoke, these aerosols, these particulates, generally speaking, they form hazes. They don't have a major contribution in rainfall nucleation. In Idaho, you get most of your rainfall nucleation from ice crystals, but also these bacterial hygroscopic nuclei from your forests, Oregon, Washington State, British Columbia, right? And so, yes, fires, I mean, I don't want to say are bad, but hey, we don't need to oxidize and burn that scale of vegetation. It's a very, very simple thing in ecology, like the whole of ecology goes back to Odin when I was young. If you can't beat it, you eat it, right? Every problem, if you can't beat it, you eat it. And basically the solution to fires is, you eat them, right? You basically say, here is fuel, and how do we eat that fuel? So how do we accelerate two options, or they're one option really, but in two forms? How do we accelerate the microbial biodegradation of that fuel into stable soil carbon so it doesn't burn, so we don't go in this negative oxidative spiral? We've got two very elegant ways of doing that. The first is herbivores, which are really just mobile compost heaps on four legs with a mouth and a business end called an anus. And basically, these things actually pick up fuel and then put it into rumen or whatever, biodigest it, and end up with biofertilizer, soil carbon, and protein that, if you're not a vegan, you can eat. And okay, so there you are. Here's a beautiful natural ecological process to avoid fires through herbivores. The other one, of course, is in situ biodegradation of litter layers by fungi and bacteria. And again, how do we restore that across the whole landscape so the fuel is actually broken down into soil rather than left up above to oxidize? And again, that's what we've been talking about. If we can create the sponge, if we can create the moisture, then we accelerate that fungal biodegradation. We reduce the fuel buildup, and of course, we reduce fires. And we can do that. Now, I mean, we feel guilty in Australia because in the 1850s, you guys came to Australia on our gold rushes. You liked these eucalypts, you knocked off some seeds and you took them back and you called it the Californian blue gum. And of course, what you did is you took the seeds, but you didn't bring any of the microbial biodegradation system, the soil fungi that you needed to do to break down that litter. And as a consequence, now in California, every 3 years, you just burn yourself to a crisp because you don't have the fuel breakdown systems, the microbiology, to remove that fuel into soil carbon. It just builds up till it burns. And so it's an enormous opportunity for Idaho, for California to say, right, how do we get together and we say, look, how do we biodegrade that fuel more actively back into soil carbon to rebuild hydrology and productivity rather than turning California into a barbecue.
All right, excellent. Yeah, that's what I was wondering. There's, I'm in an area where there's eucalyptus trees all over the place, and they're notorious. People actually go down in the forests in hills of Berkeley, and they're trying to set up they're getting FEMA to cut down 500,000 trees up in the hills because they said eucalyptus was a fire risk, and that
yeah, really, and see that's the problem. So we shoot the thing. I mean, we do need trees. Nothing wrong with eucalypts, but it's not just the tree. We've got the whole biology, and if we bring the biology, we don't have to cut the trees, because when we cut the trees, we risk going back to desert, right? And so this is always management, and all we need to do is get together and talk and understand and explore. And then there's very elegant, simple, natural solutions that are very, very profitable and very positive, right?
Yep. It's just a little bit of extra thinking instead of obliterating forests. Like maybe there's something in those forests that are important.
Yeah, Albert Einstein said you can't solve a problem with the same thinking that created it. You've got to be mongrel. Mongrel in Australia means, you've got to be a bit radical. You got to think outside, radical to the roots of the problem, and then there's a solution. Nature has all these solutions. It's worked those out over billions of years. We've just got to get smart, less arrogant, and listen to her.
So Kate. Oh, go ahead, Neil.
I'm just gonna jump in. Our time is up.
Oh, it is? Dang it.
That doesn't mean we need to stop, but we do need to stop our recording.
Okay.
So I just want to thank everybody who is here. Thank you to Walter for your fascinating presentation and for clarifying a lot for me and helping to spread the word that things are both more complicated and in some ways more simple.
Yeah. Well, look, we might stop too, because I think we've got another sort of commitment, but if there's any other questions arising, right, and please take them down, and get them to us, and we're very happy to keep that dialogue. I'll also be back in the States in April this year, and Judith and Dee Dee, so yeah, we can keep the conversation going.
Sounds
awesome.
Good.
Yeah, so feel free, if you have additional questions, send them to me, Raleigh@sustainabledesignmasterclass.com. I'll compile them into a big list. I'll send it to Walter, and hopefully he'll be able to get back to you at some point.
We can do a follow-up or something. All right. In that case, folks, if this is your first webinar with us, you can sign up at sustainabledesignmasterclass.com.
Oh, yeah, let me go to that link.
We've got about 45 other webinars. All of them up to this point, all of them deal with the intersection of ecology, entrepreneurship, and agriculture. That's what we're focused on. Later on this year, we will probably get to some architecture and sustainability, but come find our stuff, and because if this is what you're interested in, this is all we do. All right.
Yeah. And
thanks.
Okay, look, thank you very much, and thanks, all the very best, and let's keep going. Okay, soil carbon sponge. Soil carbon sponge.
We're gonna create that sponge. Just you wait. Okay, everybody, and thanks again.
This is already doing it, right?
Yeah, for sure. And we're gonna have a ton more webinars on water going through February, even into March. So just stay tuned. Your minds are got to be blown on water, and we're gonna keep going on this theme. So thanks, everybody. Okay.
Okay. Thank you. All the best.